Everybody, I think we can start now. So today we have Rafael and Martinez, Galarza from CFA coming here to talk about his work on the simulation of the SED of starburst in the galaxies. So Rafael has did his PhD at Leiden University in the Netherlands, and he has been in CFA for a few years on the postdoc.
Year and a half only.
Simulating the affiliate galaxies and starburst. And today he will show us all the basic results.
Thank you. Well, thank you, Kwang, and thank you everyone for coming. I'm very glad to be here. First time ever in Canada, first time ever at CITA, so I'm very happy to be here. And thanks to you and to Francois for organizing my visit. So yeah, before I get anyone disappointed, I will say that this is a work that is also highly observationally supported. So I did use some simulations, but there will be also a lot about observations in general. So if you're simulation geeks, I hope you won't hate me after I finish the talk. So I'm going to be talking about a project that I've been thinking about since I was in Leiden as a PhD student, and that I had finally found some time to work on recently. And it's about star formation in galaxies in general, and in particular in interacting galaxies. This is some work that I've been doing in collaboration with a few people at the CFA. Loren Lance, who's done great work with the observations, who's now a postdoc at Caltech. And Brent Groves and Chris Hayward, who have provided most of the simulation work for this project. Let me just start with an outline of what I'm going to be talking about today. So I'm going to just start with an introduction about why, in general, we care about studying starbursts and interactions locally and also in the high redshift universe, and why we bother about this in general. I will then move on to describe a little bit about our approach on how to tackle the problem of the internal physics of interactions by talking a little bit about a set of simulations we've been using together with observations to try to constrain the physics for these systems. We'll move on to describe as well a Bayesian routine that we have developed in order to fit the spectral energy distributions of these objects, including both continuum photometry and spectral information, in order to squeeze as much as we can from the data we have. And I will present the results of applying that to a set of simulated interactions as well as observations of interacting galaxies. And I will focus on a particular parameter of these systems, which is the compactness that I will define properly when time comes. And I will then try to link our more local study of these systems to a little bit the higher redshift universe and see what that can tell us about the history of star formation in the universe. So why do we care about studying star forming galaxies or interacting galaxies? And well, I would just have to say that since we live in a community that is mission-driven in the science we do, then let me remind you that JWST, which will be the next big space telescope from NASA and the European Space Agency, will have as one of its main goals to study the assembly of galaxies. So how do galaxies come to form the way we see them today? And the interesting part about it is that most of what we see today as galaxies formed has been forming over the last little bit more than half of the story of the universe from redshift about 2.5 onwards. And we know that that process of assembly is still happening today, and we see galaxies still interacting and evolving. And so it's very important for us to understand these interactions in the local universe in order to try to interpret things that are going on further away in the universe. And of course, in the way, we will also learn about what will be the fate of our own Milky Way when it collides with Andromeda. And the reason why we're interested in interactions in particular is because they might be a clue to what powers starbursts in the universe. And so before I talk about starbursts, I would like to try to define what I mean by a starburst. So the community has not come to a definite definition of what a starburst is. But you can think of it as a transient episode of enhanced star formation in a galaxy. So a lot of star formation happening in relatively reduced volumes of space at a high efficiencies. And not to define it, but to characterize it, you can think in terms of the depletion time for the gas. So basically, if you measure the total gas in the galaxy or in the system, and you see what the star formation rate is, and you calculate the depletion time of that gas according to that, and that turns out to be much less than the age of the universe, then you are talking about starburst. So as a few examples there, you have, for example, the depletion time for the Milky Way is about 3 gigayears. So still relatively large in comparison with the, relatively comparable to the age of the universe. But as you go to more and more starbursty systems, you have that time going down, and you don't need to limit yourself to galaxies. You can also talk about star-forming regions or star-forming mini starbursts within galaxies, like, for example, the 30 region or the W43 region that is very well known to some people here. So what happens is that when you see a system like that, you see that it's heavily enshrouded in dust because there's a lot of star formation going on. Thick layers of dust obscure it, and that makes it very, very bright at the infrared wavelengths because there's a lot of light being reprocessed from the young stars being reprocessed by the dust and re-emitted at far infrared wavelengths. And by studying them, we can learn a lot about the mergers themselves, but also about the process of massive star formation, because massive stars form preferentially in this kind of massive star-forming regions. And also, as I mentioned before, a little bit learn about galaxy evolution. And one of the most important observational hints that we have in order to understand these systems is, of course, their SEDs, their total spectral energy distributions. And you can see that as you move, from disk-like galaxies like M101 or the Milky Way towards more starbursty or even ultraluminous infrared galaxies like this one here, you have more and more relative contribution for the far infrared. And so we hope that by studying in detail these SEDs, we can learn a little bit about the physics of what's going on, even though in this talk I'm going to try to push it a little bit farther and try to understand not only the global properties of galaxies and their global SEDs, but what does that mean in terms of the internal physics for these systems. We have evidence that interactions are a trigger for starbursts. And we think that that's because a lot of the gas during the interaction loses angular momentum and kind of gets funneled into reduced space volumes, where basically the dynamics make it very efficient at forming stars. And of course, when we look in the local universe and we see ultraluminous infrared galaxies, they are usually morphologically very disturbed. And what you're seeing there is a comparison of some simulations by Mejos and Hernquist with real observations from the Hubble Space Telescope. And in most of these systems, we know that they are very bright at infrared luminosities, and we know that locally, at least, these superluminous systems are probably related to interactions most of the times. But the question is, can we actually relate these spectral energy distributions of these objects to the physics driving the star formation in them? And in particular, can we associate particular stages of the interactions with the star formation properties of these systems? And this is one of the questions that we're trying to answer with this question. Unfortunately, though, starbursts are very complex systems, and to show you that, I'm showing you here a photo of 30 which is a local starburst system in the Large Magellanic Cloud, and that is the typical prototype of the blocking, the single block of a starburst, which is basically a giant H2 region with a lot of young massive stars, and then young stars that are hitting the dust, ionizing all the gas around it. And so you have a lot of components. You have the stars themselves and their distribution of masses, but you have the gas, you have the dust. And when you try to understand all that mess, unfortunately, in galaxies, the problem is that when you try to look at the spectral properties of these systems, for example, with the Spitzer IRS, most of the starburst galaxies, except the very, very local ones, actually fall within, the size of the slit. And so we have to rely on integrated properties of the SED. And that's why it's so important to characterize the internal SED. Actually, JWST, when it's launched, not even JWST will be able to resolve this type of objects, at distances larger than 30 megaparsecs. So if we really want to understand what's going on in the non-local universe, even after JWST, we will have to rely on these integrated properties. Of course, one approach would be to try to understand these systems locally, and this is some work that I've myself trying to do as well, using Spitzer IRS and a couple of papers that I wrote on 30DOR and NGC 604 in an M33 before. And so we rely on the integrated SED. And as you can see in this adaptation of a figure by Daniela Calcetti, you have different components that trace the star formation in different regimes of different wavelength regimes and energy levels. So you have the far UV that traces unobscured light that just comes out of the massive stars and gets directly to your detector. As well as the H-alpha emission from ionized hydrogen. But then you have a component of obscure star formation that is basically all the light that has been captured by the dust, reprocessed, and re-emitted at infrared wavelengths. And so if you want to understand the overall star formation properties of these objects, you need a multi-wavelength approach. And then the question is, how do you relate those SEDs to the internal physics driving in the resolved spots of star formation in galaxies, this problem. So as I mentioned already, one option is to study local systems that are resolved and then extrapolate, but I'm going to take a slightly different approach here. And that approach is basically using simulations, hydrodynamical simulations of mergers, of galaxies colliding, to which you can also plug a empirical star forming law, basically to predict empirically predict what would be the star formation in those systems as they interact, and you follow them dynamically through time. And you get some observations. We also got real observations of interacting galaxies in the local universe. For both of them, we got an SED, an extracted SED in the case of the real observation, and a synthetic SED that we calculate from the hydrodynamical simulations through radiative transfer, et cetera, et cetera. I will describe it a little bit more in detail. And then we use a fitting tool based on models of the local physics of H2 regions, of these giant H2 regions within these galaxies, to try to relate the physical parameters that we get in these objects that we know very well, because we know how fast they are forming stars, et cetera, with the actual observations to try to get some new information about the physics of star formation in these systems. Of course, we know which parameters we put in the hydrodynamical simulations, and we know what we're predicting from the SED fitting, so we can compare to what extent we're doing that good and then relate that to real observations. So what we've done is, together with particular Chris Hayward, who has done a great deal of work on these simulations, we have calculated these hydrodynamical simulations for both isolated galaxies and interacting systems. And those simulations are very well described in a couple of papers by Chris. They use hierarchical tree method to compute the gravitational interactions themselves, and smooth particle hydrodynamics to actually calculate the fluid dynamics. And on top of that, we plug for above certain density threshold, we can plug in a star forming law that we use as the Smith-Kennicut law, that is basically a volume-dependent law, exponential with n being 1.5. And whatever that density is reached, we plug star formation that are happening according to that law. And then what we do afterwards is we plug whatever radiation we get from those star-forming regions in the simulations and do the radiative transfer of that radiation through the dust and gas that surrounds them, using the Sunrise code originally developed by Johnson et al., which is a 3D Monte Carlo dust radiative transfer code, so that we can generate synthetic SEDs for these interactions during different stages of the actual interaction. And we do that for 4 progenitor galaxies, and this you can find well described in the paper by Laurent Lance this year, where that cover a significant range of mass, with also different number of particles, et cetera, and these progenitor galaxies are basically chosen to describe what we actually see in local galaxies, so that we know that we are comparing, at least in terms of mass and total luminosity, the objects that we want to study with the real counterparts. And we follow their dynamical, evolution all the way from when they first approach through, several, passages between their center of masses until they finally do coalescence and enter a post-merger stage where they would be star forming passively. And that can last between 2.5 and 6 gigayears. So we do all the possible interactions, the 10 possible interactions between these systems, and we follow all of them in time in order to see how their SEDs evolve. As for the observations, we also obtained SEDs by combining a suite of observations at a broad range of wavelengths all the way from the UV, using mostly space-based observatories, but also some ground-based in the near-infrared, to obtain photometric points at all these different wavelengths, and that includes, of course, most recently data from the Herschel Space Telescope that we've reduced for these galaxies in order to obtain, the shape of the SED and the far-infrared wavelengths, which is what interests us the most. At this point. So this is just an example of some of those galaxies for which we have obtained the photometry. And an interesting thing to mention here is that they cover a broad range of interacting stages, all the way from pretty much isolated galaxies like this one, where maybe there is some degree of morphology disturbance because of an early interaction, all the way to very morphologically disturbed systems, where you see that there are two or more nuclei that are interacting, in this case of 4038, and you see how in the particular case of the infrared wavelengths, you can trace all the star-forming regions there for these systems. But what we actually do is we obtain the integrated SED, photometry for each of these total emission for each of these systems, and in that way we can build the spectral energy distribution for them. In this case, an example just from AO1, where we have different contributions from older stars, young stars, either in the UV or in the far infrared here. There is also some contribution from cold dust, meaning that not all the dust is being heated by very recent star-forming activity, but also older stars that are not necessarily young and strong in UV field can also contribute to the dust heating. And that way, this is what we use to try to interpret the physics that we see there. This is just to show you a match between the observations and the simulations. So basically, the bars here are the interacting and isolated simulations that along the interaction sequence will cover a range of luminosity, and also the stellar mass range that we cover over 2 orders of magnitude. And the stars there are the simulations that the catalog of simulations that we have obtained. In this particular work, we've been focusing on this on the red diamonds there that you see, and you see that there's a relatively good match between observations and simulations in terms of the mass and the range of luminosities that we cover for these objects. So that was important in order for us to being able to apply any conclusions we get from this to the actual masses and luminosities of the systems that we observe. So what's next? So we have synthetic SEDs, and we have observed SEDs from interacting galaxies, and now we want to try to understand that in terms of the internal physics of star formation. And so we need some model of what the evolution of the internal ISM is in these systems. And so we fit the SEDs using a particular model. A particular thing I should mention here regarding the fitting is that rather than just doing just a chi-square minimization of this, so we start from a pre-calculated grid of SED models that we try to fit to these observations or simulations. But rather than just doing a simple chi-square minimization, we just apply a Bayesian technique in order to get probability distribution functions for the parameters based on their likelihoods, but also based on any information that we had collected independently about the physical parameters, in order to obtain not only the best chi-square values for the fits, but just all the information we can get in terms of how likely the different values for the parameters are based on this study. This is because most of the times when you just do chi-square minimization, you're limited by the amount of data, the generalities in your models. So you want to know how this probability distribution function look like for the different simulations in order to actually make sure how unique your solution is, whether there are local maxima of probability, there are not absolute maxima, et cetera, et cetera. So that's the approach we get. And as for the models that we use the models originally developed by Mike Dopita and Brent Gross for star-forming galaxies, which basically assume that your starburst or your star-forming galaxy will be a collection of individual H2 regions. Each of those H2 regions has, it's massive. This is like the picture I show of 30 Dor. It's massive stars that are, blowing up all the gas and ionizing the dust. And it has, of course, an H2 region around it of ionized gas, but also a PDR molecular envelope around it. And we calculate the dynamical evolution of that spherical situation, basically by assuming that this is like a mass loss bubble that expands, driven by the radiation pressure of these guys. And consistently, we calculate the radiative transfer for that situation. And we let it evolve, this collection of H2 regions over 10 million years, which is the time where most of the massive stars start to die out and the UV field starts to decrease. But because the slightly older populations up to 100 million years can also contribute to the dust heating and to especially the near-infrared fluxes, we also account for further evolution up to 100 million years. And we do the radiative transfer for both the H2 region only, and also a fully covered situation of the PDR around it. And then we can calculate a covering factor by linearly combining those two extreme situations. Yes?
Dynamics there. So you're assuming, is it basically a adiabatic wind tunnel expansion law that's each of these ones is involving, and it's sort of a definite shell radius that's expanding until the ISM pressure?
What you're actually measuring is the radius of the boundary of the H2 regions and as it expands, and basically this is all driven by the mechanical radiation force from the central stars. So this is not different from the typical mass loss bubble treatment in the Castor 75 paper, which basically describe this kind of mass loss bubbles that expand in time. But after all, what you will get from that will be just the average values of those values, because you're making a time average, and you will get average values for the radius, etc., etc.
Follow-up question: in another paper by Dopita and collaborators, they had to reduce the total wind luminosity by a factor of 10 in order to get agreements with the line properties of their H2 region population. So is that an element of this as well?
This is related with the fact that even though the spectral lines, the atomic lines that we get, that we model by using this approach, greatly help us in constraining some of the, the age, for example, of the stellar population, all these things. It is true that the spectral lines are the least well modeled of all this. We do very well at doing the continuum stuff, but you do have to be careful with interpretation. A good thing is that when you add the spectral lines, and this is something I unfortunately won't be talking to today, but in the papers I mentioned, my papers from 2012, and that we actually take the Spitzer spectrum and try to constrain the physical parameters using the spectrum lines. And even though we're not very good at predicting the exit fluxes of the lines, they greatly help us in constraining the stellar ages. So basically, if you add the lines to the continua, you actually get better answers to your the PDFs of the age mass degeneracy kind of completely shrink when you do that. So you're right that you might not get it right, but at least the ratios help us greatly in constraining this. So we do all the dynamics and the radiative transfer in a self-consistent way, and that's how we get the output SED. Just very quickly, we start, of course, with Starbus 99 stellar population synthesis to predict the input SED and energy input from the stars. This is basically, as I was mentioning, the evolution of the radius of the bubble as a function of time for different pressures. And one thing I didn't mention before is that we also include a component of ultra-compact H2 regions, where will be very massive stars that are still embedded in dust and that will have a hotter component of dust that is necessary in many of these systems to explain the mid-infrared SED. We include those as well. And what we get out is basically different, H2 regions at different ages that we can average on time. We can see what the impact of the covering fraction of PDR is on the SEDs, and of course also what the impact of the older stellar populations, more in the near infrared wavelengths there, that you can see there's an impact. However, one of my favorite parameters, or at least the one I've been looking at most carefully, is the compactness. And intuitively, you can understand compactness as, on average, how close the dust will be to the ionizing and heating sources. And so you can understand that as a struggle between, the cluster mass. The more massive the cluster, the more it will try to expand and throw away your dust, and the ambient pressure of the ISM that tries to confine it. And so a balance between those two will set basically what that will set. A given value of that compactness parameters will set the evolution of dust temperature with time in your expanding H2 region, and the effect that will have on the SED will be a shift, of the far infrared peak according to the so in terms of the global SED parameter, the compactness is a very important characteristic of this. That is not only telling us about the dust temperature, but about how that temperature relates to the internal physics of the expanding H2 region. In other words, if you have larger compactness, it's either because you have more massive clusters somehow, or more pressure from outside that tries to confine it more, or both. And we're trying to figure out what is the case as we study these interactions. And as I was saying, we do this in a Bayesian way, and so we use Markov chain way in which we calculate the probabilities for the parameters as from the likelihoods that we derive from the chi-square distributions, but that include any priors that we know on the AV, for example, or on what the values of pressure should be. Most of the priors we use here are very flat and uniform, but we can include tighter constraints if we think it's convenient. And well, this probably you all know, basically it's a Markov chain to try to step across the parameter space so that we start moving towards regions of more and more probability, and then the final sample we get, we associate to the probability distribution function. So summarizing, what we have is some observation, either a real observation of a simulated SED. We have some models that of the evolution of the H2 regions. Some priors, depending on how much information you know about individual parameters, and we get probability distribution functions for the compactness, the star formation rate, PDR fraction, AV, stellar mass, and fraction of embedded star formation as traced by these ultra-compact H2 regions I was mentioning before. And what we do is we go ahead and fit all the simulations across the whole time of the interaction, but also the observations. And we do that in the case of the simulations also for different viewing angles of these simulations. And what you get is a fit. Sure, well, you could easily get a fit, but well, more than a fit, well, you get certainly, and what you see there is that the different components. So this light blue component would be the H2 region plus PDR, and this would be the older stellar populations, and this one here will be the very recent ultra-compact H2 regions that add up to the mid-infrared. And of course, how much each of those components contribute to the total SED will depend on the stage interaction. These are three systems in different interaction stages. But this is just to show you how the fits look like. We do exactly the same for the simulated SED, and we have pretty similar residuals. But more importantly, we get, well, probability distribution functions for the parameters, in particular compactness. We get a pretty nice PDF that, according to where your system is in terms of the interaction stage moves up and down here. And what we are using to characterize it is not the best fit value, that is the one shown here and corresponding to this dashed line, but actually the peak of the probability distribution in order to characterize the different properties. Of course, we know that these are not completely realistic descriptions of the galaxy. For example, we're assuming that we're looking at systems that are dominated by recent star formation. And so, for example, we don't have, at the moment, we're adding it, but at the moment we don't have, contributions from even older stellar populations that would have a significant contribution on optical and mid-infrared. So we have to think carefully about what this is actually tracing. Is this, for example, really tracing the star formation rate over the last 100 million years, or that's actually tracing something else? And we can do that because we're lucky enough to have the simulations. And what you see there is the evolution of the blue line is the evolution of the star formation rate along a simulation. This is in particular the interaction of the two most massive galaxies in our progenitor sample. So this is a first encounter here. This is here where they kind of coalesce, and then they come to a passive stage. The red dots are the star formation rate, instantaneous star formation rate, meaning 10 million year old star formation rate that we get from fitting our H2 region models to the simulations. We get a factor of 2 or so overestimation of those values that we think is related to the fact that we're not accounting for additional heating from older populations of stars. But overall, as you can see here, this is a plot for all the simulations, and this is a comparison, all the simulations at different snapshots in time. And you see that the instantaneous star formation rate that we get that we know from the hydrodynamical simulations and our empirical law, correlates pretty well with the value we get from the fitting. You might wonder what this thing is here, and that's actually something I wanted to mention specifically. By the way, this other blue line here, red line here, it corresponds to this component, the red component we get from the fit. This one, the older stellar populations, which is not really tracing the star formation rate because it's accounting for whatever was there before, and it's actually doing a very well job tracing the total stellar mass of the galaxy. So what we have is something that traces very well the total stellar mass of the galaxy, and something that traces the instantaneous star formation rate, which is good because that way we can calculate specific star formation rates or star formation rates per unit stellar mass. But what I wanted to mention is that these points here correspond to post-coalescence. So basically after, but only in the most massive interaction. So when you take the two most massive galaxies and make them collide, what will happen is that right after coalescence, there will be a quick quenching of the star formation rate from the simulations. And if you just use, this is from the Chris paper, but it kind of shows exactly the same as I am showing you here, is that after coalescence, we are overestimating the star formation rate. And that's, again, in particular, dramatically after coalescence, when there's no more star formation going on, but the older populations are still there, and you are assigning any infrared emission there to star formation when it's actually being heated by older stellar populations. And this is what this corresponds to. So you have to be careful about post-coalescence and post-starburst before you interpret your results. This is just exactly what I say. We're just overestimating after coalescence in massive interactions. When we use the far infrared diagnostics, we're overestimating the instantaneous star formation rate by a factor of up to 100 in some cases. So you really have to be careful there. What about compactness? So here I'm just showing you what we get from the simulations again. And this is interesting because what we're getting is that there is an interesting correlation between the instantaneous star formation rate that we derive from the fitting of the simulated galaxies and that compactness parameter I was telling you about. And this is color-coded according to the mass, the total mass of the interaction. So there seems to be a correlation between those two, but this is the normalization of that correlation seems to be depending on the mass. So if you want to make it mass independent, since from the modeling and the fitting we get both the instantaneous star formation rate, but also the total stellar mass of the system, you could rather calculate the specific star formation rate here and plot that against compactness. And even though you get a kind of a certain dispersion here, that you end up with a correlation that is pretty independent of the mass there. And that correlation is important because it's linking the compactness that is related to the internal physics of your H2 regions to a global property of the galaxy that is the specific star formation rate. And so, so this is basically the contribution of these two components, the older stellar population and the young, infrared derived from the infrared. And that's what I was mentioning, that what this is really tracing is the total stellar mass in the system, as I was showing in this plot here. And so that ratio, really what this is telling you, this other ratio here is telling you about the specific star formation rate. So star formation rate, recent star formation rate over total stellar mass. And so a specific star formation rate. That's interesting. There are many reasons why I think that's interesting. The first one being that in an unresolved starburst, if you look at the SED, this is something that people have argued. Can you actually characterize the interaction stage of the SED, of the system from just looking at the SED only? And I think you can to a certain degree, because you could relate, if you look at the evolution of time here. So this is accounting for many different times of the interaction. And so usually systems start here before they interact, and they go somewhere up here, and then after coalescence they go back. So this is really telling you something about where your system could be in the interaction sequence. Of course, how high they get depends on the total mass of the interaction. But it's possible to characterize at least the specific star formation rate happening in an unresolved starburst galaxy or interaction, just by looking at the SED to some degree of accuracy. And so that's very important. So now,
star formation rate, the specific star formation rate has to do with the inverse free-fall time, and the compactness has to do with your terms of pressure. But in your models, it's really
right.
It's affecting the growth of the regions. So
right.
both measures would be density.
Right. To some degree, because mean density will not be the only thing that will be affecting your compactness. For example, what if you have a top-heavy IMF, for example, and so your radiation pressure is higher, or your right. This is exactly what we'll try to discuss now regarding how we interpret this thing. But that's precisely the point. We're trying to really figure out whether this is just a natural thing that comes out of the global properties of the galaxy and the overall pressure of it. You actually need to plug any internal physics in order to explain all of it. So here, what I have plotted is the same thing again, and this time color-coded by how much of that young ultra-compact H region component you need, meaning that this is also correlated with the younger. So the more starburst you get, the more embedded star formation rate you have. And the green points here are the observations. So the color-coded thing here are the simulations, and the green points there are showing you the actual observations in the same diagram. And an interesting thing is that, even though I don't show it there, but it's interesting because there is also, even though it's a weaker correlation, there is a correlation also between in the observations between where these points are here, where these galaxies are here, and the interaction stage. So, for example, these galaxies like 3031 are somewhere down here, whereas very morphologically disturbed systems go up there. Like 3690, which I think is the one with the highest compactness we get. This one here is M82, by the way, and so this is an interesting. So there seems to be some kind of evolution of the compactness along the interaction sequence, and what we're trying to figure out is whether you can interpret that in terms of the internal physics. So the other thing I wanted to mention here about this plot is that there seems to be kind of a turnover here of the correlation for low star formation. Of course, you will have a limit of the specific star formation rate that will make it turn at some point. But it's also interesting to point out that these points here are mostly post-coalescence points. So basically, when you have quenched star formation, and what you might be getting is only the most compact remainers of the H2 regions, because most of the other gas and dust has been consumed or blown out. So this could account for that kind of over-prediction of the compactness for these systems. But it's nevertheless interesting to see that there's kind of a turnover there in that correlation. Now, why would this be important in terms of the overall picture of star formation across the history of the universe? And this might be relevant to a discussion that has been going on in terms of a correlation. This is from the work of Benjamin Magnelli and his collaborators, who have obtained basically different at different redshifts. They have measured the dependence of dust temperature in galaxies with specific star formation rate. So it looks like there is some kind of evolution of the across the history of star forming in the universe between the properties of the star formation rate and the dust temperature, and that has led to people believe that there might be different modes of star formation, which I will discuss later. But nevertheless, there is a correlation between dust temperature and specific star formation rate measured also at higher redshifts, and we're trying to link these results from the local universe with those studies a little bit farther away. So I'm sorry that he left, but I wanted to point it out about regarding whether you could say that the compactness correlation comes only from overall, density of the ISM. For example, do we get higher compactness in more luminous systems just because clusters are closer to each other and they are hitting each other mutually, hence increasing the compactness as you would expect from the hydrodynamical simulations? Or do you actually need to include internal physics? And here I'm plotting the observed galaxies again, this time color-coded by star formation rate density, so basically star formation rate divided by the total area of these systems. And the correlation is not necessarily straightforward. I mean, there are systems, for example, that have very different star formation rate density, but are closer in the compactness specific star formation rate diagram. And there are systems that are very close in specific star formation rate, like these 2 points here, in the star formation rate density, but far apart in the log C star formation rate. So just the density of clusters in the galaxy, I think, would not be enough to explain that correlation of compactness that you see here. And so I think what we need to do is to include some of the physics that we have in the modeling of the H2 regions to explain that correlation. And a possibility around that would be to, for example, say that if your compactness, which is defined like that, is proportional, logarithmically proportional to your specific star formation rate, then must be because your cluster mass, for example, and the pressure are also proportional to your specific star formation rate. And you could so this one, so the cluster mass being proportional to the specific star formation rate, you can argue about it. There are some simulations that show, for example, that if you assume that the cluster mass would be somehow associated to the molecular cloud mass, original mass, and some simulations show that, for example, a paper from a couple of years ago, I have the reference there, the molecular mass of these clouds would be related to the gene mass, to the gene's mass of these systems, and that gene's mass would be correlated to the star formation rate in this system. So you could argue that this could hold, and so you have to figure out about how the pressure would depend on star formation rate. It will also depend on the density, and so this alpha factor could depend, for example, on the IMF of the system, etc., etc. But in any case, you could characterize this in terms of the star formation rate efficiency, and in terms of, for example, the IMF of the system. So there is a way, since we cannot completely explain this with the global physics of the dust and with the proximity of clusters, I'm arguing that some of this could be related actually to the internal physics of the ISM, and this is a very relevant thing. And why would that be relevant? Well, when people look at the famous two different modes of star formation rate, so this is from the work of David Elbaz a couple of years ago, they took a bunch of galaxies at different redshifts, up to 2.5, redshift 2.5, and they just stacked them all to the same rest frame so that they could produce kind of an average SED. And they separated them by basically the fraction total, the ratio of total, total infrared luminosity to luminosity at A microns. And they found two different populations. So a population that basically stays close to this value, and then some outliers here that have a higher value of that ratio. And they argue that these are the starburst-like star-forming galaxies, whereas this is what they call the main sequence of the galaxies. And when they looked at systems belonging to the main sequence, then they found that they have a particular SED that is colder, and that has stronger PAH emission, but also corresponds to systems that are, globally more extended, whereas the starburst component, the starburst systems that were those outliers there, these ones here, they have hotter SEDs, less PAHs, and when they look at them, they are more compact. So they are arguing that these are systems that are, more compact, globally compact, and that they have a different mode of star-forming regions. And actually, the Magnelli et al. Paper relates that to different conditions in the ISM going on in these two systems. So that's why I think the study of the compactness in these two different type of systems will tell us whether or not the conditions of the star formation rate, of the star formation physics, are different in the starburst versus the main sequence. First of all, is there really a separation between a main sequence and starburst? And you can have your doubts about it, and I think this is what we're trying to answer. So what we did was we also took those average spectra from Elbaz et al., the main sequence and the starburst, and tried to fit them with exactly the same models that I have described in this talk, and try to locate those points here in this diagram. Once again, the color blue and red colors here are the simulations. The green points are the local interactions, and this here happen to be what you get when you try this fitting with the average spectrum of Elbaz. So either a bunch of main sequence galaxies and a bunch of starburst galaxies. They seem to follow a similar, 2 points, but okay, they seem to pretty much look like in the same line, but somehow the normalization is different. And a way to interpret that, of course, is that if it's actually true that at higher redshifts, because one thing that I didn't mention about the main sequence is that locally, most very luminous systems, what we call ultraluminous infrared galaxies, most of these very luminous systems form stars in the starburst mode, whereas it looks like in the high redshift universe or intermediate redshift universe, most ULIRCs are actually in the main sequence. So they don't form stars in a starburst mode, but in a disk, spread situation. So basically, the way you could interpret that is that at higher redshift, the compactness is lower in these systems, meaning they are actually, these galaxies, the counterparts of these galaxies in the high redshift universe, are more, they might be more luminous, but they are also forming stars in a more spread way rather than compact. So this is exactly where we're at the moment, trying to relate those two. And a good thing to do here would be to, of course, populate this diagram with more observations, not only of interacting systems, but also of really, really luminous objects to see if this continues, or that reaches a limit here. But also resolved starbursts, because we want to know to what extent this extends down to systems that are very low mass, but that contain the physics that we're trying to model. For example, the W43 region on 30 Dorados. Try to locate those points in this diagram as well to try to figure this out. And I guess this is where I would like to end. So basically, what I was trying to convey today was there's a lot of precious information hidden in the SEDs, integrated SEDs, and we just need to learn how to squeeze as much information as we can from them for unresolved systems. For galaxies in post-coalescent, if we just use the regular, IR, infrared diagnostics, we are usually really overestimating the star formation rate significantly. There is also a correlation between the specific star formation rate, compactness, and interaction stage in local systems. And by characterizing the slope of that correlation, we hope we can learn a little bit more about the physics of the internal processes happening also in the high redshift universe. For example, the IMF or the star formation efficiency in these galaxies. And this is where I want to leave this talk. Thank you very much. And if you have questions. Thank you.
So it's a bit late. If you have any questions, go on.
Well, I think one of the main goals was looking at the SEDs and you are doing the engineering, actually the reverse engineering now. You simulate the galaxies with the parameters that you know, and you are trying to understand how the SED of the starburst galaxies are different, for example, to the negative surface galaxies.
Correct.
And as I understood it, that only the pH emissions that you see from the SEDs are almost different.
Mm-hmm.
But can we also just look at the SEDs from two unknown galaxies and say, okay, this is starburst, this is Mason?
Well, no, what I showed with the pHs was kind of a statistical effect. So they basically took many galaxies for which they have some photometry, but they were at different redshifts, and they put them all to the rest frame. And so you get kind of a fake spectrum of the average main sequence and a fake spectrum of the average starburst. And you see that on average, the pHs in the starburst case are lower. And you could relate that. You could claim that that's basically because on average, the dust is closer to the ionizing sources in those systems, and pHs could get destroyed in the stronger UV fields. But I think that the specific study of the spectra of these objects will add very valuable information. In particular, we're trying to actually add the IRS spectrum for these systems and see if, for example, in an effort to actually link all this discussion to the internal physics rather than just to the global gas dynamics, we want to see whether the spectral line ratios, the atomic spectral line ratios, would, for example, favor a stronger radiation field in starburst-like objects, etc. And that the pHs will also be important in that respect. So yeah.
I think we better go up and have some coffee. So you can have more questions. Thank you.
Well, thanks for coming. Thank you.